Hello, chemistry students. I'm going to finish up part 2 of the notes here about how pressure affects the phase of matter. And it does affect the phase of matter, even though we never think about it. All right, so if the solid is less dense than the liquid, added pressure will cause melting. Okay, the only common example of this is water. So like when you go out and you go ice skating, like you probably never thought about, I wonder why it's like the water melts under the ice skates. Well, it's because you increase the pressure, and that the way ice forms, the water molecules arrange in these hexagonal patterns that leave a lot of space in between. So when you put pressure on them, it squeezes them out of that hexagonal pattern and causes the water to form a liquid. That's also why water is less dense as a solid than it is as a liquid. All right, so if the solid is more dense than the liquid, which is pretty much everything else, added pressure causes the liquid to freeze. Right, and increased pressure always affects gases by making them more likely to condense. Now, let's look at some phase change diagrams and talk about some stuff, because this is... Alright, so let's talk about what normally happens when you start out with a chunk of ice. So, let's say you have a chunk of ice, and, well, let's do this first. We got to be able to identify where solid, liquid, and gas are at on a phase diagram, so that's pretty easy if you can remember some basic things about matter. So solids are more likely to exist when it's cold and when the pressure is high, because that squeezes the molecules together. So the combination of low temperatures, look at the chart here, pressure on this side, temperature on this side. So low temperatures are on the left and high pressures are near the top. So that combination is going to give you a solid. Then, if you increase the temperature, the solid melts. And if you increase the temperature some more, then it boils and forms a gas. All phase diagrams, if there's pressure on the axis here and temperature on this axis, are going to go solid, liquid, gas. The liquid's going to be sandwiched in between the solid and the gas. The solid's going to be in the higher pressure side, and the gas is going to be on the higher temperature side. Now, with that said, let's start out with some solid ice at standard pressure. And if you are doing this at regular atmospheric conditions, you're going to be at a pressure of 1 atmosphere, and it's going to stay at a pressure of 1 atmosphere. So if you increase the temperature, the pressure remains constant, and lo and behold, what happens? You change from solid to liquid. That's melting, okay? No matter how you do it, if you go from solid to liquid, that's melting. Then if you increase the temperature some more, pressure continues staying the same, then you change from liquid to gas, and that is boiling. Now, let's say that you're out ice skating and you have some ice that's frozen. It's at a temperature below 0 degrees Celsius, and that ice is, just chilling out there on top of the ice skating rink, so the pressure on it's about 1 atmosphere. And then you go across it with your skates, which put all of your weight on a very thin, small area. So that increases the pressure. Well, what happens? You change from solid to liquid. That's melting. So you can cause the phase to change by changing the pressure. Another one that is a cool demonstration is I can have some water at room temperature, and I can lower the pressure of the water, and that lowered pressure causes it to change from liquid to gas. Now that shouldn't be super surprising to you, even though it probably would be if you watched it in class, but you know that liquids, like, they have the high altitude cooking directions for ramen noodles, for example. Well, the reason why that's there is because liquids boil at a lower temperature at higher altitude because there's less pressure. So the extreme of less pressure is a vacuum, like space. So if you were to take your helmet off in space from your spacesuit, you would shortly before you passed out and all that stuff, you might feel the sensation of the water on your tongue actually boiling, which is a story from an astronaut that actually was accidentally depressurized while he was suiting up. So water can boil at low temperatures if the pressure is low enough. And then there's also this point called the triple point, where solid, liquid, and gas can exist all at the same time, which you can think about that as being like ice water that's at a low enough pressure to boil. Okay, let's look at the phase diagram for carbon dioxide, because carbon dioxide is kind of weird too. So carbon dioxide is used as dry ice, and let's see if we can figure out why it's dry. So again, apply the solid, liquid, gas thing here. So the liquid's going to be in the middle, solids at high pressures and low temperatures, gas at high temperatures and lower pressures. Now, we're going to take our solid dry ice at standard pressure, 1 atmosphere, and then we're going to heat it up, and watch what happens. It changes from solid to gas, and we learned earlier that that change is sublimation. Okay, no liquid in there. Why? Well, at atmospheric pressure, carbon dioxide just doesn't exist as a liquid. It doesn't have strong enough intermolecular forces to exist as a liquid. If you wanted to see some liquid carbon dioxide, you'd have to raise the pressure to, maybe 10 or 20 atmospheres. And then you could get liquid carbon dioxide. But you'd also have to be still pretty chilly, like the critical points at about 30, 35, somewhere in there. All right, so here's another one. So if we took our solid carbon dioxide and we increased the pressure like we did before with the water, oh look, nothing happens here. So it's still a solid. All right, so something that you'll notice here in the difference between these phase diagrams is that if there's a negative slope to the line between solid and liquid, that means that the liquid is more dense than the solid. And if there is a positive slope between the interface between solid and liquid, then the solid is more dense than the liquid. All right, so just a few terms for you here. The normal melting and boiling points are the melting and boiling points of the substance at standard pressure, or 1 atmosphere. So those are the ones that are commonly reported, like 0 for the melting point of water and 100 degrees for the boiling point of water, Celsius, by the way. Then the triple point is the temperature at which, and the pressure combination at which all 3 phases, solid, liquid, and gas, can coexist together. I've already talked about that example of ice water that is boiling. And the critical point is the temperature beyond which a substance cannot liquefy. This is referred to, or the substance is referred to as a supercritical fluid beyond this point. So there was the critical point on the carbon dioxide diagram. So some sources report the supercritical fluid as being everything to the right of that temperature. Some sources report it as just being the part up here that's kind of above this point in pressure and above this point in temperature. And some kind of have a blend of the two. So just know that the critical point, you don't get liquid beyond that critical temperature, and it's something between a liquid and a gas, but it certainly has fluid properties. All right, so I think that wraps up this video. Thanks for watching.